So chapter 6 deals with bonding. It also deals with nomenclature. So we will get on this. This stuff is not on the first exam, so this will start kind of second exam material, I believe. Which our first exam is coming up next week. Yeah, 1 week from today, I believe. All right. What? I believe it is. I think that's what I said it to, or sometime next week the homers do. So should hopefully be that day, I believe. All right. So we're going to talk about chapter 6 here. Like I said, chemical bonding and nomenclature. So we're going to start with the nomenclature part first. Nomenclature is really the way that we name things, and there's some different ways that we go about naming, depending on really what type of compound we're dealing with. And there's really two classes of compounds that we will talk about here. There's ionic compounds, and there's really covalent compounds, which are sometimes also referred to as molecular compounds. And the difference between these two, as we'll talk about more in this chapter, is ionic is always a metal and a non-metal. And the result of when a metal and non-metal get together, based on those periodic trends in chapter 4, we will get the metal to transfer an electron or two or more over to the metal, non-metal, and the result is the metal will make a cation that's positively charged, which I think we've talked about some cations and anions in the previous chapters. Non-metals will be anions, which are negatively charged. And again, the main difference here is there's absolutely no sharing of electrons in an ionic compound. What we have going on is what's referred to as electrostatic attraction. Is basically opposites attract is what holds that together. So the positive charge of the cation, the negative charge of the anion is really what holds that together. Actually, that bond is really a strong bond, and it gets stronger with the charges. So something +3, -3 is actually held together a lot stronger to something that's like a +1, -1 sort of attraction between the two. Different than that is covalent molecules, which are really two nonmetals together. And when we get two nonmetals together, what happens is because they are pretty much located on the same spot on the periodic table, they share very similar properties in terms of what they want to do with electrons. And really what nonmetals want to do with electrons is keep theirs and get some more. So what happens when they do get together is the best that happens is they go, well, I'm not giving up my electrons. And clearly you're not giving up your electrons. So what happens is they decide to actually just share electrons. So what happens when we get two nonmetals together is there's some sharing of electrons. And as we will talk about later in this chapter, the sharing may be equal sharing or it may be unequal, but there is some aspect of sharing of electrons that occurs when two nonmetals get together, and those are what are referred to as covalent compounds, are molecular compounds. So that's the main sort of difference between those two. And again, we'll get a little bit more into it when we get to the bonding part here in just a bit. Any questions so far? All right, so then let's talk about naming. There are some things that are just really have common names that people use all the time. And I would say for the most part, these first three are really the ones you should focus on. H2O is water. It is not a trick question. Yes, so just put water, move on with your life. It'll be okay. Yes, so just put water down. It is not like dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide, right? They would much have a refreshing glass of water. So we do use, obviously, water for H2O. NH3 is ammonia. And it should not be confused with something else we'll talk about, which is ammonium. And it looks very similar in terms of their formula. CH4 is the simplest organic molecule you could have. It's methane. It's like what comes out of the Bunsen burner there when you turn on the gas and you light it on fire. I would say these other ones, for the most part, you don't have to worry too much about. Most people will call NaCl, sodium chloride, kind of their more formal name and stuff like that. But definitely those first three are ones that you should definitely go by a common name and stuff like that. So as I mentioned there on the front page, we really do break this off into two different categories, ionic compounds and covalent compounds. And depending on what happens, we do name them slightly different. So really the first thing that you want to do when you're sort of approaching maybe naming something or trying to write a formula is really to figure out what type of compound you're dealing with. Are you dealing with an ionic compound? Are you dealing with a covalent compound where we have sharing of electrons? Because there is sort of two distinct ways that we go about naming those guys. And even with ionic compounds, there's actually kind of two ways that we go about naming those as well. So again, it is the metal and non-metal transfer of electrons with an ionic compound and two nonmetals with a covalent compound. Whenever a metal is involved, one thing that you should keep in mind, whenever a metal is involved, for the most part, it's kind of the most important thing that's in that compound. A lot of times the metal is really determines how you go about naming that particular compound. So definitely you got a metal, non-metal, and an ionic compound. Always look to the metal as the way to sort of figure out how you should name these guys. So when we talk about cations and anions, again, they are our positively charged guy, which is usually our metal, and our anion, which is our nonmetal and negatively charged. And we're going to really start talking about type 1 and type 2 compounds, and those are ionic compounds. So again, this is always going to be sort of for an ionic compound. And when we look at these things, we do sometimes need to name just the cation or maybe just the anion. So when we have a cation, if we were just to name the positively charged ion, it is simply just the element name. So if we have something like sodium with a +1 charge, that would be the sodium ion. If we had something like calcium with a +2 charge, that would be the calcium ion. We had something like hydrogen, H+, that would be the hydrogen ion. Now, if you're asked to name an ion like this, a cation such as this, that is how you would go about naming it. If it's positive, you just simply use the whole element name. Also, if you were asked to write the formula for a cation, that is what it should look like there on the left. It should have the symbol and the correct charge for it. So if you're asked to write a formula for an ion, it should not just be the symbol by itself. It should have the appropriate charge. For anions, it's a little bit different the way we kind of go about naming those guys, which are negatively charged ions. We actually, for those guys, take the root of the nonmetal name. We drop the last part, or even a little bit more than last part, and we add IDE to it. So we basically drop off the last part of the element name, put IDE in the place of it. So if you had something like O2-, that's oxygen. This would be the oxide ion. If you had Cl-, that is chlorine. This would then be the chloride ion. And one of the only elements that can really kind of go both ways, can be positive in certain cases, can be negative in certain cases, is hydrogen, which is -1 in this case. And that would be our hydride ion. So negatively charged ions gets the IDE at the end of the name. And once again, if you were asked to draw the formula for an anion, that is what it should look like. Again, it should have the symbol, and it should also have the appropriate negative charge on it. So if you're ever asked to write the formula for either a cation or an anion, or any ion, which would be one of those two, you should always include the charge. First off, any questions on that? Now, that is sort of different than when we actually put these two things together. When we put these two things together, they actually will end up with kind of no charge. So when you're writing the individual ions, they should have charges, but when you do put them together, the overall charge should equal 0. Thank you. When you do put them together. Speaking of charges, I think we might have talked about, but just in case we did not, let me just refresh here on a periodic table. Now, there are certain things on the periodic table, or certain elements on the periodic table that do have fixed charges. So let's just make sure. Let me draw a wonderfully drawn periodic table, also known as a big rectangle. So that's going to be group number 1. So everybody in group number 1 will form a +1 charge. Everybody in group number 2 will form a +2 charge. Just kind of squeeze it right there. Then we have 3, 4, 5, 6, 7, and 8. So continuing on to group 3. That's just an extra bonus line there. Group 3, it's really aluminum what we're looking at here, and that guy will be a +3 charge. Sometimes people include gallium, which is underneath it, but really it's aluminum there. Those are all positively charged because they're all metals, so they typically will lose electrons and become positively charged. Now, remember that there is that sort of staircase where our metalloids are kind of coming down through that part. And there's really no good pattern in group 4, so we do kind of skip group 4. But starting with group 5, the nonmetals, which are above the staircase, like nitrogen and phosphorus, they typically will make a -3 charge when they do make a charge. Group 6, like oxygen and sulfur, will make a -2 charge when they get a charge. Group 7, all your halogens, your fluorine, your chlorine, all those guys will make a -1 charge. And again, those are our nonmetals, which will gain electrons, which is why they will make those negatively charged. So we do go +1, +2, skip the transition metal, +3 at aluminum. We skip group 4, and then we go backwards, -3, -2, -1. Again, the non-metal region. Now, the transition metals, for the most part, can form a variety of charges, so they can have a variable positive charge. It kind of depends on the situation as to what charge they will have. There is 3 exceptions in the transition metal region that actually do have a fixed charge, and that is our friends zinc and cadmium, which is somewhere about there. When they make a charge, it will always be +2. And then if you hang a leftover there by cadmium, our good friend silver there will make a +1 charge. So even though these 3 here in this sort of backwards L are transition metals, they will always have a fixed charge. So that's really important in terms of naming, to recognize that those guys will have a fixed charge. Now, everybody else in the transition metal region, which is all this, and even outside the transition metal region and this region below the staircase, they are still metals, and they can have a variety of charges or a variable type of charge. So even things, common areas like our lead and tin and antimony, those guys sort of in that area, bismuth, these guys can have variable types of charges. So when we talk about naming, they're sort of clumped in with the transition metals as to how you go about naming them, because they could have a variable charge. Any questions on that there? Okay. So also, by the way, things only do get charges when they combine. So when a metal and non-metal combined, that's really when something gets a charge. Before that, they don't have a charge. So things like, sodium metal has no charge. Chlorine gas has no charge. It's just when they come together to form an ionic compound, that is really when they both really gain a charge and stuff like that. I'm sorry. Row 4, there really is no good pattern in this area, because above the staircase you have nonmetals, on the staircase you have metalloids, and below the staircase you have metals. So there is no real good pattern there, because you really have a combination of all 3 types of elements. The good news is below will be really more like metals, and you'll treat those like the transition metals. Above, if it's carbon up there, it'll most likely be named as a non-metal, which means it won't have to worry about charges or anything like that. Other questions? All right, so definitely keep that in mind as we go through here. So what is the difference between type 1 and type 2 compounds? As I mentioned before, type 1 and type 2 refer definitely to ionic compounds. And again, as I mentioned a number of times, that is a metal and a non-metal we're dealing with here. And 100% of the time, that is the most important one, which is the metal. If it is a type 1 compound, what that means is the metal has a fixed positive charge. So as we just talked about, That's going to be everybody in group 1, 2, 3 are silver, zinc, or cadmium. So as soon as you recognize two things, you should look at the compound you're looking at to name, if you're naming it, and should go, all right, that is a metal, that is a non-metal, that tells me it's ionic. I look at the metal, it's in group 1, 2, 3, zinc, cadmium, or silver. That is a type 1 sort of compound. And then you would proceed to name it, as we'll talk about in just a second, how to name it type 1 compounds. If you look at an ionic compound and you look at the metal and non-metal, and you see the metal is not in any of those groups, it's basically a transition metal, or as we just were talking about there, just to the right. That should click in your head that that is a type 2 compound, and you need to go about naming it as a type 2 compound, which obviously we'll talk about in just a second on how to properly do that. So some examples of type 2 metals are transition metals like chromium. In certain cases, chromium can have a +2 charge. In other cases, chromium can have a +3 charge. Copper, in certain cases, could be +1 or +2. Iron, same deal. Iron very commonly could be +2 in certain situations or +3. The real deal about why we have to do a little bit extra here on our type 2 is we really want to tell people what the charge is on the metal. So you got to kind of inform people. In this case, we're talking about the guy with the +3, or in this case, we're talking about the guy with the +2. The reason we don't have to worry about that with type 1 compounds is it's always that charge. You will never find a sodium with anything other than a +1 charge. So it's like a known quantity. There'll never be anything different. So you don't really have to go out of your way to go, hey, this is sodium with like a +1 charge. You don't have to worry about that because it has a fixed charge. Any questions on that there? And we're going to obviously talk about each of these in just a second as to how to name them properly. So these are some examples from your book there, some ions. Again, everybody's positive here, just the whole name. Everybody here gets the IDE treatment. The other really important thing about when we put together a positive ion and a negative ion to make an ionic compound and write the formula for it is it should always be the positive guy first, followed by the negative. So it should always be cation to anion, both when you write the formula and also when you give the name. So always positive and then negative guy is the proper order. The other really important thing is whenever we take anything that is positive and put it together with a negative ion, we want to make sure that the overall charge when we do that is 0. So like all the charges balance out to perfectly 0. And we want to do that in the simplest way that will get us to 0. So you want to make sure that you put them together in the simplest way to get 0. So for example, if I had a sodium ion and I had a sulfide ion and I wanted to put this together properly in a formula, if I just stuck them together, one of each, would I end up with a charge? The answer is yes, because if I take +1 and -2, I'm left over a -1, which is not what we're looking for. So in this case, we want to put them together in such a way that the overall charge equals 0. So we could clearly see that I actually need more of the positive guy to do that, right? So I really need one more sodium to get that accomplished. That gives me a +2 charge that will balance out the -2 charge just coming from the sulfide. And that means that if I were to write the formula, it would be Na2S would be the proper formula. The formula, when we write it for the compound that has both the positive and negative guy, should never, ever have a charge. Yeah. But it is made up of two things that do have charges. It's made up of the cation in this case, which is the sodium ion, and it's made up of the anion, which is the sulfide ion. But whenever you put that metal and non-metal together to write the proper formula for an ionic compound, you should never, ever have a charge. So there should never be a charge when you put together, but you do need to remember it actually is two things that do have charges. So if I had something like calcium ion and say the phosphide ion, why don't you write what the proper formula should be when you put that together? Okay, so if I want to get this to 0, in this case, I'm putting something that's a positive 2 together with a -3. The common number between those two numbers is 6, and you get that by simply multiplying them together. Yeah. So if you multiply those numbers together, that will give you the simplest way to put them together that you get a 0 charge. So really at this point, what we've got to figure out is how to get both of them to 6. So right now, calcium's sitting at +2. So really, I need not one of them, not two of them, but I need 3 of them, right? That will give me a +6 if I pop 3 of them in there. Phosphide has a -3 charge, which means to get this guy to -6, I need 2 of them. And now we are balanced out, +6 and -6. And hey, I could just count what I just drew there, right? So I got 3 calciums. So we're going to put the 3 there. Number always goes to the guy to the left. Yeah. So this number always goes to that guy. And I have 2 phosphorus, which looks like that. Yeah. And again, that goes there. So that would be the correct formula there. Yeah. Question on that? Yeah. Question? All right. So let's say we had Al3+ and Br-. What should be the proper formula when we put that together? Need more, which one? The Br, right? And if you weren't sure, you can multiply those two numbers together. 3 and 1 is 3 is where we want to end up, right? So we don't need one of the Br-, but we actually need 3 of them. That will give us a -3. That will balance out the +3 charge that we see on the aluminum. And that means that the proper formula is we just have 1 aluminum and we have 3 of the Brs. Yeah. Okay. Any questions on how to put those together correctly? If it helps you to draw them out like I'm doing, it's a good idea. Do it that way. Yes, I do it that way. It makes it easier. You just count it and then you don't have to worry about it. Now, I will caution you that sometimes people are taught, hey, just move these things down and up. And that works, 90-ish% of the time. So if you're good with that, you could do that. It doesn't work 100% of the time. So I would not no-brain it and just kind of move things up and down. Again, you'll get lucky in a lot of cases, but there will be a number of times where it will not work out correctly. So, sometimes it's helpful just to think of it like balancing out the charges correctly here. All right. So let's get into how we actually name these different types of compounds. We're going to start with type 1. Which is an ionic compound. So once again, that is going to be our metal and non-metal. And once again, we're really going to ignore everybody else except for the metal part. And that is going to come out of our group 1, 2, 3, our silver, zinc, our cadmium. They basically have a fixed charge. So once you're able to recognize that it is a type 1 compound, your job's pretty much over at that point. You just need to name it correctly. And the way that you name it correctly is simply use the whole name of the metal. And then you lay up the non-metal name where you get rid of the back part and replace it with IDE. And that is it. Nothing else should be added. Don't add extra stuff. Yeah, so just do what it says. So for example, we did a couple there on the previous page. I think we had this guy here. So we look at this guy. That is sodium, which is a metal. That is sulfur, which is a non-metal. That automatically should tell you ionic compound. I want to then look at the metal. Metal is sodium, which is group number 1 on the periodic table, which should automatically tell you it has a fixed charge. That should then tell you, let me use the right finger there. That tells you that this would be a type 1 compound, which means I'm ready to name at this point. So I'm going to name it. First name, there's the whole name of the metal, which would be sodium. Second guy is sulfur, which drops the last part and becomes sulfide. That is it. Yes. Any questions on that there? Now, there is a 2 here, and people like to use prefixes like, hey, it makes it look more chemistry-like. It's going to make it look like an X when I grade it. Yeah. So do not do it. Yeah. Doesn't matter how many you have of either one of those. You should never, ever, let me say it one more time, ever use a prefix in an ionic compound when you're naming, unless you like crossed out things on your paper. Don't do those things. You shouldn't use it. Again, sometimes people always like to do it Again, makes it look a little more scientific-y and all that kind of stuff, but do not do it. So that means that if I had something, say, like this, what should the name of this guy be? So we take a look at this. That is calcium, which first off is a metal. That is chlorine, which is a non-metal. So that is ionic compound. I look at calcium. I look at the periodic table. I find calcium in what group? Group 2, which means it has a fixed positive charge, which tells me it's a type 1 compound. That's all I'm thinking about at this point. I'm ready to name. So Ca, we're going to use the whole name, which means it will be calcium. And then the nonmetal gets the IDE. This would be calcium chloride, IDE. Once again, we're not going to use prefixes after what I just said a second ago, I hope. So again, it doesn't matter if there's 2 there. It doesn't matter if there's 40 there. It doesn't matter if there's 300. I don't think you'll ever get 300 there or 40, but it doesn't really matter. It is just the name of that nonmetal with the IDE at the end. The reason we do have a 2 there is the cation here is calcium with a +2 charge. The anion in this case is chloride with a -1 charge, by the way. Chloride is not Cl2 minus, it is actually just Cl minus. The 2 means that you don't have one of them, but you have 2 of those Cl minuses. So sometimes people want to include that 2 on the anion, and that would be incorrect. Question on how to go about type 1 here. Yeah. Good rule of advice is don't overcomplicate it. Yes, keep it simple. So it is important, though, as we talked about, to remember that when we put it together, no charge, but it is really, again, made up of 2 things that have charges. So when we look at Ki, that is a metal, that is a non-metal, that is group 1, which means it is ionic and it is type 1. So that's why we just roll with the whole name of the metal and IDE on the non-metal. This is, though, made up of a cation. That should be potassium with what type of charge? K+, as is group 1. And the anion formula here would be I- because iodine is group number 7, and it should have a -1 charge. That's also why when we put them together, we just need 1 of each of them. Yeah. Any questions on that there? All right. Well, now that you're professionals, there we go. I feel like I got a lot of extra dots in there. All right. So let's do some names of these guys here. And I tell you what, let me give you some names and you write some formulas. Let's do, I don't know, let's do some sodium oxide. Let's do an aluminum. Let's do an aluminum something. Let's do an aluminum. Let's do aluminum bromide. All right, so proper name on the left there, proper formula on the right. Maybe I'll add one more for fun. It's always fun, maybe. Magnesium or not, I don't know. Magnesium. Let's do magnesium phosphide. All right, take a few minutes here. Like I said, names on the left and formulas on the right. Okay, let's take a look, see how you're doing. So once again, first thing you want to do really is identify what you're dealing with. So we see potassium, which is a metal. We see Cl, which is a non-metal. So once again, it's going to be ionic. We want to look at the potassium, and we could find on the periodic table in group 1, which tells us it has a fixed charge, and that means that it is type 2. So that's really all we need to think about at that point. We're going to use the whole name of the metal, which is potassium. And once again, here, our chlorine will get the IDE treatment at the end, and that would be potassium chloride. Question on that? Again, is made up of 2 ions. The potassium ion is the cation, and the chloride there is the anion. So those are really the 2 things that make that guy up. Coming to the next one, we see calcium, which is a metal. We see bromine, which is a non-metal. So once again, that's ionic. We look at the metal, which is calcium in group number 2. So it has a fixed charge. So we know it's type 1. And now we're ready to name. We're going to use the whole name of that metal, which is calcium. And again, the bromine will get the IDE treatment. We can get the spelling there going. Once again, we're not going to worry about in terms of naming the 2 that is there. And this is made up again of 2 ions. That is the calcium ion, which is the anion, the cation, and the anion is bromide, which looks like that. And that's why we have the 2, because we need 2 of them to balance out the overall charge. Question on that one there. Coming here, that is barium, which is a metal. That is hydrogen, which is actually a non-metal in this particular case. And barium is group number 2, which means it has a fixed positive charge. So that is also going to tell us it's a type 1. So we're ready to name this, which is barium. And this is really the negative version of hydrogen. So this would name it the same way, hydride, IDE at the end of it. The cation here is barium with a +2 charge and 2 hydrogens, each with a -1 charge, which would be hydride in this case. That is really the only time hydrogen will really be negative is when it comes after a metal. So when you see a metal and then hydrogen, the hydrogen is going to be negatively charged. In all other cases, pretty much hydrogen is going to be positively charged. Any question on any of those names there? All right, so now we have some names and we want to write the formula. We still want to kind of approach it the same way. Sodium is a metal, oxide is oxygen, is a non-metal. So we know it's a ionic compound. We know sodium is group 1, which means it's a type 1. So sodium, which is group 1, should have a +1 charge. Oxide, which is oxygen, is group number 6, which means it should have a -2 charge. Once again, we're going to put these guys together to equal 0. That means we do need 1 more sodium to balance it out. That gives us a grand total of +2 to balance out the -2. So the correct formula here, Na2O, would be our correct formula. Any questions on that one there? Looking at aluminum, which is a metal, bromine, which is a non-metal, again telling us that it's ionic. Aluminum is group 3, which means it has a +3 charge. Bromide is group 7, which means it has a -1 charge. So once again, when we put this together, we need more. Which one? Yeah, we need, again, in this case, 3 of them. That gives us a -3 charge to balance out the +3 charge. And now, like I said before, I could just count what I got going there. I got 1 aluminum and I got 3 of the BRs, right? And again, we put the number on the bottom there. Yeah. Any questions on that one? Lastly here, magnesium, which is a metal, phosphide, which is a non-metal, which is really phosphorus on the periodic table. Magnesium is group 2, so that's going to be a +2. Phosphorus is group 5, which means it is a -3. The common number there we need to get to in this case is, we need to get to 6 again, right, to get us to 0. So to get the phosphorus to 6, we need 2 of them. To get the magnesium to 6, we need 3 of them, right? That gives us a +6 to balance out the -6. And once again, I'm just going to write what I got going on there. So that is magnesium. I have 3 of them. And phosphorus, I have 2 of them in that case. Any questions on naming or writing formulas? Need to be able to do both. Yes. Any questions? Okay, so this is type 1, and this is always metal, non-metal. Metal has a fixed charge. So let's talk about what happens when we have an ionic compound where the metal does not have a fixed charge and how we go about naming those guys. Very good. Yeah. So those are type 2 compounds, and type 2 ionic compounds, which is what they are. So they are still ionic. They are still the metal and non-metal together. And once again, I don't really care about the nonmetal. It is the metal that is the most important thing here. The metal will be a transition metal, are just to the right, like lead, tin, etc. And what makes them type 2 is they basically can have a variable positive charge. So really the only difference that you have to do in this type of naming is you need to figure out what the charge is, and you need to tell the person what the charge is on the actual metal. So the way we go about naming this is we still use the whole name of the metal. We still use the nonmetal, gets the IDE at the end of it. The only difference is in between, we do a Roman numeral. And what the Roman numeral represents is the positive charge on the metal. Not the grand total of positive charge, but if you took one of the metals out, what the positive charge is on one individual metal. So that is what the Roman numeral means. It is not how many you have, which is a very common mistake people make. It is actually just one individual metal in that compound, what the positive charge is. So if we look at the example that we have there, I'm just gonna borrow some of the room here. So if we look at this guy here, the first thing we want to do is approach it the same way. That is a metal, which is iron, Fe. Cl is a nonmetal, so it tells us it's ionic. I'm going to look at the metal, and I can find iron dead center-ish of the transition metal region. So that automatically should tell you it has a variable charge, and it is a type 2 compound. What that should tell you is you need to figure out what the charge is on it. So what we know is we do have an iron that has some type of positive charge. The way you're going to be able to do that is you will always know 100% of the time the charge of whatever it's attached to. So you'll always know that charge. So if we look at Cl, that is group number 7, which means Cl has what type of charge? -1. And there's not one of them there, but there are 2 of them there. That gives us an overall charge of -2, which means to balance it out here, the iron needs to be +2. So now we're ready to name it. Now that we figured out what the charge is, we're going to lay up the whole name of the metal, which is iron. We're going to put in there a Roman numeral 2, which indicates the actual charge on the positive metal. And once again, the last part's going to be like normal. That will be chloride. So that is iron 2 chloride. Once again, absolutely no worries about that in the name, and no prefixes in the name for this one as well. The reason we have to use the Roman numeral is something like iron. If I had something like this, FeCl3, what would this name be? It would be. So we still have the iron, which we're not sure, but in this case, there are 3 Cls, and that means we have 1, 2, and 3. That's a -3, which means in this case, the iron is +3. So this guy's name would be iron Roman numeral 3 chloride. And again, it is for the charge on the positive guy. So because it could have multiple charges, frankly, you need to tell people, hey, this case is the 3, this case is the 2, and that is what the Roman numeral is there for. You do not need to do that in type 1, like I mentioned, because sodium can never, ever be anything other than +1. So there's no need to hammer it into somebody's head that it is +1, because it cannot be anything other than +1. Question on type 2 there, type compounds. All right. Then what is this name of this guy? PB, by the way, is lead. Can be found underneath the staircase in the same row as carbon. It is not a transition metal, but is named the same way as a transition metal. So PB is lead, and it should be named the same way. It is a type 2 compound. What is the proper name here? All right, what do we think? This name is lead, numeral 2. There more to that? Oxide. Everybody agree? All right. So this would be a situation where, frankly, you'll get one of those because that is incorrect. Yes. So let's work it through the right way here instead of doing this move. Yes, because that's the wrong move, by the way, just so you know. So in this case, lead is a metal. Oxygen is a non-metal. Lead is, again, outside the transition metal region, but underneath that staircase. So it's still named the same way. So it is going to be a type 2, which means I'm not sure what lead is. But I do know oxygen is group number 6, which means what type of charge does it have? -2. And there's not just one of them there, but there are 2 of them, which means the overall negative charge here is, which means the lead should be +4, which means the correct name here should be lead Roman numeral 4 oxide. And you don't get the X with that one. It's not, we don't throw that in for free here. So it is 4. This is what I was saying earlier. If you just blindly cross over, which a lot of people teach, nothing wrong with it. A lot of people teach that move, but it does not work in all cases. So it's good to think about it in terms of balancing charges. And if you just kind of draw it out like I did, you'll figure it out correctly. And that's really what you're aiming for there. But again, if you just blindly do it, and again, a lot of people do teach it that way, you'll be okay 90-ish% of the time. If that's okay for you, you'll be okay, but they will not work 100% of the time. Any questions on how we got to lead 4 there? It was if you were asked, for example, in this situation, to write the formula for the cation alone, just a positive guy. The correct thing that you should write in this case would be Pb with the actual charge by itself. If you were asked to write the formula of the anion, in this case, it should be O2 minus. And both of those things should always have charges if you are writing them separate from each other, just the ion by itself, not combined. But once you do combine them together, you should write it, over here. You should write it where there is no charge. So when they come together, they should have no charge, and they should have no charge in the simplest way to get them there. And in this case, we would actually need 2 of those guys, and that's how we get to the proper formulas here. So whenever you put a metal and non-metal together in a formula, no charge should be written, but the charges should balance out to 0. But if you're asked, and sometimes you are asked to just write the positive ion by itself, not with anything else, or a negative ion by itself with nothing, those formulas should always have the charges. That was your question. Question on that? Yeah. All right. And again, you should, if the other question was, should you move it this way or this way, you could do that, but it will not work in all cases. And this is one of the cases where it will not work properly. Yeah. Other questions? Okay. All right. Fun with naming. That's good stuff. There is an old way of naming, which we are not going to use here, but sometimes it does still sort of show up where they use really the origin of the name for the element. Like iron is ferric or ferrous, or copper is cupric or cuprous. IC for the guy that has a larger charge, OUS for the one with the smaller charge. We will not use it. I just say it because it does still show up occasionally in manuals and stuff like that. We will strictly use Roman numerals for type 2 compounds when you name them. But don't be surprised, especially with iron and copper, they like to use ferric and ferrous and cupric and cuprous. So here's a table of all those guys. So these are the formulas for the ions. And as you can see, each of those formulas, because they're not attached to anybody else, has charges associated with them. And again, we want to use the appropriate Roman numeral. One of the weird ones is actually mercury. So this is mercury. And this is mercury. And oddly, the one right here that has a lot of 2s is mercury 1. So the one with all the 2s is mercury 1. And the one with only 1 2, oddly, is mercury 2. And that's because mercury 1 comes as what is referred to as a dimer. It's really 2 mercury 1s stuck together. And that's why there's a 2 on the bottom. So to realize if it is mercury 1 or mercury 2, usually this 2 will still hang out as you look in a formula. So if you had something like this, versus something like this. That 2 comes from here, so that top guy would be mercury 1. There is no 2 here, which means that would actually be the mercury 2 in this case. So mercury is kind of a weird one. It has a bunch of 2s, and that's actually mercury 1. And the one that has only 1 2 is mercury 2. Everybody else is not too bad in that sense, but you do have to figure it out, and you can figure it out based on whatever it is attached to. All right, so as we've been talking about, to name type 2, we want to use Roman numerals to indicate the positive charge on the metal. So why don't you give some a try here? So give the proper name for each of these. I think I got them all. And we'll also do some formulas here. So let's do iron 3 oxide. Let's do chromium 4 bromide as well. All right, so left-hand side, let's give the proper formula, proper name, and right-hand side, proper formula. Let's see what you come up with here. Let's see how you're doing. So again, we'll identify what we're dealing with. CO, which is cobalt, which is a metal. Cl, which is chlorine, which is a non-metal. Once again, whenever a metal is involved, that is who you want to look at in all situations where metals are involved. That is really the one you need to take a peek at. Cobalt's there in the transition metal region, so that should tell you it's a type 2, which means we need to figure out the charge. So once again, if you're just going to want to draw it here, we do know Cl is group 7, it has a -1 charge, and there's 3 of them, which gives us a -3. That means our cobalt there should be +3, and that means it should be whole name of the metal, cobalt, Roman numeral 3 for the charge. And once again here, regardless of how many we have, it is just going to be chloride at the end of it. Yeah. Any questions on that one there? Coming here to copper, which is a metal, iodine, which is a non-metal, so that tells me it's ionic. Once again, metal most important, which is copper, which is number 29 there on the periodic table and in the transition metal region. That tells you it is a type 2. So maybe we don't know off the top of our head here what copper would be, but we do know iodide is group 7, which means it has a -1 charge. So here to balance it out, simply copper needs to have a +1 charge in this case. And that would then give us whole name of the metal, copper, Roman numeral 1 in this case for the charge. And once again, iodide here, IDE for our non-metal. Any questions on that one there? This is tin, which is a metal. That is bromine, which is a non-metal. Tin is not necessarily in that transition metal region. It is kind of under the staircase just to the right. And that also means that it's a type 2 compound. So same idea here. Tin, I'm not sure maybe what it is, but I do know bromine is group 7. And there are 4 of them there. And that means obviously here, that's going to give us a -4. And that means that the tin needs to be +4 here to balance it out. And whole name of the metal, which is tin, Roman numeral 4 for the charge. And once again here, bromide for the bromines, regardless of how many we got going on. Any questions on any of those names or how we got there? All right, so now we're going to go backwards using the name to write the proper formula. So when I see iron Roman numeral 3, that tells me the iron has what type of charge? Positive 3 seems like a good answer, since that is what the Roman numeral stands for. So you don't even have to figure it out. It actually tells you in this case what the charge is. Oxide is oxygen, which is -2. So once again, this is an ionic compound that has ions. We want to put it together to equal 0, the simplest way possible. That means we need to get to 6 in this case. +3 and -2 will get us to 6. We do need 2 of the iron 3s because that will then give us +6. And we need 3 of the -2s. That will give us -6. And now we just need to write what I just drew there. That is 2 irons and 3 oxygens. Yes, and then we should be set in that case. Any questions on that there? Lastly here, chromium, Roman numeral 4, chromium is Cr, and I know it is a +4 charge because of that Roman numeral. And bromide is bromine, which is group 7 on the periodic table, and it has a -1 charge. So once again, to put these together to equal 0, we're going to need more of our Brs, and a grand total of 4 will get us there. And that means that we have CrBr4 would be our winner. Any questions on any of those there? Our type 2 compounds. So ionic compounds are broken up into these 2 types. Type 1, no need for Roman numeral because the metal has a fixed charge. Type 2, need the Roman numeral because the metal has a variable charge. And in no situation prefixes in either of those. Yes. Any questions on any of those? All right, so that's basically what we just talked about there. That's basically what it says. All right. That was a good talk. Let's get to type 3 then, I think. We're going to come type 3 binary compounds. Now, type 3 compounds are different. These are actually 2 nonmetals together. They're sometimes called covalent compounds or molecular compounds. And there is no transfer of electrons. There's no ions in this case. Everybody is sharing electrons in this case. They are 100% the easiest to do. And they are also 100% the ones most people screw up on because they want to do a bunch of stuff they should not do. Now, I know you've been waiting all night for it. This is prefixville. Yes, this is where we use prefixes. This is the correct situation to use prefixes. Like mono is 1, right? Di is 2. Tri is 3. Tetra is 4. I can get it there. Penta, we'll get it. 5. Hexa is 6. Hepta is 7. Octa is 8. Nona, maybe I'm making it up, is 9. Deca is 10. So we do use prefixes here. We put the name basically the way the formula is written. So whatever element comes first in the name, and whatever element comes second in the name. So when we go to name these, there are a couple of rules where we use our prefixes. We do not use mono on the first name, but it is okay on the second. So we don't use mono on that first one, but it's okay to use on the second. The other very common thing that happens with these prefixes is the prefix and the first letter of the element will sometimes end up with a couple of vowels that come back to back. So if we get a vowel combination where we have an O from the prefix and an O from the element name, we usually drop the O from the prefix. We have an A and an O, A from the prefix, O from the element, we drop the A. So we do not do those type of things. So other than that, 2 I's are typically okay, but the kind of double O or double A in a row is not okay. So for example, I got my good friend CO here. That is carbon, which is a nonmetal. That is oxygen, which is a nonmetal, which tells you it is type 2. No, it is not. It tells you it's type 3. And the beauty of that is you do not have to worry about charges. You don't have to worry about balancing anything. You pretty much just need to pick the right prefix and use the right naming. So what is the right naming? We use the prefix if necessary and the whole name of the first element. Then we use the prefix and the second element gets the nonmetal IDE treatment. So prefix on both if necessary, maybe not the first, but prefix on both. And Second guy gets the IDE like everybody else. First guy, just the whole element name. So to do that here, we have C, which is carbon. We have O, which is oxygen. And we have how many carbons? 1. So the prefix for 1 is mono. Should I use it on the first name? So it's just going to be carbon in this case. We have how many oxygens? 1. Can I use it on the second name? I can. So that would be mono. Second element gets the IDE like we were doing with type 1 and type 2, oxide here, right? IDE. This is a situation where I just backed up a couple of O's on top of each other. We do not call it carbon monoxide, right? We die from carbon monoxide poisoning, not carbon monoxide poisoning, right? So we actually do drop the O from the prefix. And the correct name here should be carbon monoxide, 1O. Any questions on that there? So like I said, these are really the easiest. There's nothing to figure out other than pick the right prefix and put them into the name. And you should be done with these in like 2 seconds. If you're taking much longer than that, you're doing way too much work. Yeah, you don't want to do that. You're going to talk yourself into something that's wrong. I just have a feeling about that. So if we do a little N2O action here, we'll try a little, you know, I don't know, we'll do some SO2. We'll do a little everybody's favorite N2O5. SF6. All right, give the names of those guys. Okay, let's take a look. So we look at the first one. That is nitrogen, which is a nonmetal. That is oxygen, which is also a nonmetal. So at that point, you should be really happy. It's a type 3 compound. No need to worry about anything but some prefixes. So we definitely have 2 nitrogens. So the prefix for 2 is di. And we again use the whole name of the first element. So that would be dinitrogen. This is oxygen, and we have only 1. So we can use mono on the second name, but we are going to drop one of the O's there. So this would be dinitrogen monoxide. Yeah. Any questions on that one? Yeah. This is sulfur, which is a nonmetal. That's oxygen, which is a nonmetal. I'm ready to roll into naming at this point. I got 1 sulfur. Should I use mono on the first name? No. So that's just going to be sulfur. 2 is di. And once again, oxygen does get the oxide, the second element. So that would be sulfur dioxide in this case. Yeah. Nitrogen nonmetal, oxygen nonmetal. 2 for nitrogen there will give us again dinitrogen. Prefix for 5 is penta, and that oxygen then becomes oxide. That's going to give me an AO situation happening. So we're going to drop the A from the prefix, and this will be pentoxide without the A because we don't get that A and O sort of combination. Lastly here, that is sulfur, nonmetal, fluorine, nonmetal. So no mono on that first one. So that's going to be sulfur. Prefix for 6 is hexa and a little fluoride. Yeah, there we go. Question on any of those there. By the way, if you have a name like trioxygen, pentabromide, and I might have just made that up. I probably did. What should the formula be, by the way? So as soon as I see prefixes, I should know it is a type 3, which means I don't have to do anything but write what it says, right? So tri is 3, oxygen is O, so that's an O and a 3. Penta is 5, bromide is Br, so that's a Br5, and I'm done. Yeah, so it's even quicker going that way. It actually tells you what to write. So don't overthink these for type 3. Don't try to balance things. It is just the appropriate prefix. No mono on the first one, good on the second one. Watch the couple of vowels that come together. At any point, did we do any type of Roman numerals with these? No. So if you find yourself Roman numeraling and prefixing, which people like to do because that's ultra chemistry, it's wrong. Yeah. So prefix only for type 3 nonmetals, Roman numeral only for type 2 ionic compounds that need it for the charge. Type 1, none of it. Yeah, just the name and the IDE. Any questions on that? All right, we're laid up there for today.